For the continuous function f of x, it can be represented by the power series of this form. For the first n power term, this is called the Taylor polynomial degree n. Then the rest of them we call the remainder term and use the notation Rn. Or we can write it as the f of x equals the Taylor polynomial of the degree n plus remainder term. The absolute error would be the absolute value of the f of x minus the pnx, or the exact minus the approximate, which is the absolute value of the Rn, or the remainder term. Definition: let Pnx be the Taylor polynomial of the order n for the function f of x. The remainder in using Pn to approximate f at the point x is In equals f of x minus Pnx. Theorem, or the remainder theorem. Let f have continuous derivatives up to the n plus 1 derivative on an open interval I containing x equals a. For all x in I, f of x equals to Pn plus Rn, where Pn is the nth order Taylor polynomial for the f center at x equals a, and the remainder is Rn equals the n plus 1 derivative of the function f at the point c divided by n plus 1 factorial times x minus a to the n plus 1 for some c between x and a. Estimate of the remainder theorem. Let n be a fixed positive integer. Suppose there exists a number m such that the absolute value of the n plus 1 derivative of the f at the point c less than or equal to m for c between a and x inclusive. The remainder on the nth order Taylor polynomial for f centered at a satisfy this expression. The absolute value of the Rn, which is the absolute value of the f minus p and x, less than or equal to the m multiplied by the absolute value of x minus a to the power n plus 1 divided by n plus 1 factorial. Examples. Given the function f of x equals the natural log of 1 minus x, find the remainder term Rn for the nth order Taylor polynomial centered at a equals 0 for the function f of x. Express the result for the general value of n. The formula for the Rn is the n plus 1 derivative of the function f at the point c divided by n plus 1 factorial multiplied by x minus a to the power n plus 1. For this case, a is 0, and the value c is between x and a. Now we are going to find the pattern of the n plus 1 derivative of the function f on the side notes here. Since the function f of x equals the natural log of 1 minus x, the first derivative is 1 over 1 minus x multiplied by negative 1, or negative 1 to the multiplied by 1 minus x to the negative first. The second derivative is negative 1 multiplied by negative 1 multiplied by 1 minus x to the power negative second multiplied by negative 1 by using the chain rule. Or we can rewrite it as negative 1 to the power second multiplied by negative 1 times 1 minus x to the power negative second. The third derivative is negative 1 to the second multiplied by negative 1 multiplied by negative 2 multiplied by 1 minus x to the power negative third multiplied by another negative 1. And rearrange the term, consolidate the negative 1 and negative 1 to the second as negative 1 to the third. And we can see this as negative 1 times negative 2 times 1 minus x to the power negative third. Keep going to see the pattern. For the fourth derivative, we obtain the negative 1 to the third, negative 1, negative 2, times negative 3, times 1 minus x to the power negative fourth, and multiply by negative 1, or write it as negative 1 to the fourth times negative 1, negative 2, negative 3 times 1 minus x to the power negative fourth. Looks like we have the pattern of the nth derivative. But find one more to confirm the pattern, like the fifth derivative of this function. We will get negative 1 to the fourth times negative 1 times negative 2 times negative 3 times negative 4 times 1 minus x to the power negative fifth and multiply by another negative 1. Consolidate or rewrite it as negative 1 to the fifth multiplied by negative 1, negative 2, negative 3, negative 4 multiplied by 1 minus x to the negative fifth. As we see the pattern, since the second derivative, we have negative 1 to the power second, negative 1 times 1 factorial of 1 minus x to the power negative second. For the third derivative, we get negative 1 to the third multiplied by negative 1 to the second times 2 factorial times 1 minus x to the negative third. The fourth derivative, we get negative 1 to the fourth times negative 1 multiplied itself 3 times. And the rest gonna be the factor 1 times 2 times 3 or 3 factorial times 1 minus x to the negative fourth. For the fifth derivative, we get negative 1 to the fifth multiplied by negative 1 to the fourth multiplied by 4 factorial multiplied by 1 minus x to the negative fifth. For the product of negative 1 to the fifth, negative 1 to the fourth, that is negative 1, same as the rest of them. And then we can summarize as a pattern of the nth derivative of this function as negative 1 multiplied by n minus 1 factorial multiplied by 1 minus x to the power negative n, or write it as negative 1 multiplied by n minus 1 factorial divided by 1 minus x to the power n. We're gonna need the n plus 1 derivative. So n plus 1 derivative of the function at x equals negative 1 multiplied by n factorial divided by 1 minus x to the power n plus 1. And then we use this in the formula for the Rn. Therefore, the Rn equals the n plus 1 derivative at the point C, which is negative n minus 1 n factorial. Sorry. So the formula for the Rn, or the remainder of the nth degree polynomial Pn, would be Rn equals the n plus 1 factorial, or negative 1 multiplied by n factorial divided by 1 minus x to the power n plus 1. And this divided by n plus 1 factorial, which is the same as multiplied by the reciprocal, and then multiply by x minus a, which is x minus 0, to the power n plus 1. Therefore, this is f n plus 1 at the point C. So since the n plus 1 derivative at the point x equals negative n factorial over 1 minus x to the power n plus 1. At c, we have the n plus 1 derivative at c equals negative n factorial divided by 1 minus c to the power n plus 1, where c between x and 0, which is the a value. Now we're going to replace the fn plus 1 at c into the Rn formula. So the Rn or the remainder term is the fn plus 1 at c, which is negative n factorial divided by 1 minus c to the power n plus 1 divided by n plus 1 factorial is the same as multiplied by the reciprocal and also multiplied by x minus a, which is x minus 0 to the power n plus 1. Now we get the formula for the Rn. Since we already see some common factor here, n plus 1 factorial is n plus 1 multiplied by n factorial. So we can reduce n factorial and n factorial. The formula for the Rn becomes negative x to the power n plus 1 divided by n plus 1 multiplied by 1 minus c to the power n plus 1 as a general term of n.